All right, it's Tuesday, week 5 here. Um, I hope you were nice to the substitute, to the TAs on Thursday, and you got through the lab there. And we'll do a lab again this Thursday. Um, I switched up the labs. This week we're actually supposed to do the lab on the command line stuff. And last week we're supposed to do the lab on making what's called a half adder. But the half adder is a circuit. We have to wire up this complicated circuit on your Pi. And it's, from my point of view, the hardest lab in the whole course. So I decided to switch that to this week since I'll be here and the TAs all be here. So this week's lab is probably going to be the hardest lab of the whole course. If you can get through this week's lab, everything else is easy there. So that's what's up. And so we will see a little bit of command line stuff this week too that's related to last week's lab for that. Um, so let's start. I'm going to just go into the readings and video and just talk a little bit about that. So again, we're going to talk about chapter 4 here and look at that. So I'm going to bring up chapter 4 of our text. And this just talks about computer system components. It's like kind of, we've been looking kind of at the CPU and that sort of stuff. This is like anything outside of that. And it's a pretty broad topic. And so we'll do a lot of show and tell, talk about some old stuff, talk about some new technology, see how things have changed and evolved here. It's interesting to note that most of the stuff we are talking, the textbook talks about is how to wire stuff to your computer or your device or whatever. There are different ways of wiring something to another thing. And my question is, when was the last, how often do you wire something to your device or something like that? I've now made the big leap, in recent years. So these are my headphones. I was just on a plane this last week. I had to travel, and so I have actually wired headphones I had to get out to use on the plane, and it made me think, when was the last time I used wired headphones with a headphone plug? Do you remember those? They're not that old, right? You've done wired headphones with a headphone plug. When was the last? Do you still have wired headphones with a headphone plug, or have you gone Bluetooth with your headphones? So yeah, yes, I'm Bluetooth on all or most of my devices now and stuff like that. My computer, my laptop, I still use a USB headset for microphone stuff. I still use that, but my daughter still laughs at me every time I Zoom with her because I have them big. And so I see she says, "You got earbuds? Why? They have a microphone built in them. Why don't you just like?" Oh well. So when we're going over this, think of that. How much of this is now out of date because, and what is this? What has it been replaced with as far as wireless kind of technology for this? So as we get away from the CPU, the first thing we look at is memory. That's the closest, fastest thing is the RAM there. Because again, we talked about there are inside the CPU, there are these registers, some memory, just limited memory inside the CPU for things. But once we get out of that, we have memory there. And I was trying to find I have a little example of core memory, which is these little magnetic cores in this grid of wires there. And I couldn't find it for class today. I was very disappointed. I don't know where it went here. But in the old days, we used these core memory stuff. And then we developed this digital memory that wasn't physical. Like the magnets actually physically rotate these little tiny magnets, these little core, they look like little tiny donuts that rotate. But now then we moved to this digital kind of method. And again, we're not going to go over how this sort of memory works so much. We talked a little bit about NAND gates and AND gates and adders and stuff like that a couple weeks ago, and this kind of works on this same sort of technology, but I'm not going to. So you can kind of see our voltage is needed to here, and we regulate it, and we have some input voltage, and then that stores in these gates here. And again, for this to work, we need the voltage to be continuous here for this memory to be active. That's why when your computer shuts off, you'll lose whatever's in your memory, generally, in your RAM, if it's not something that can be stored without static memory here. And so again, I'm not going to go over too much about the functions of these DRAMs and stuff like that. But how does it look? What does it look like in the computer here? If I can change this to. Yeah. Okay, so generally it's going to look like a chip these days, like this sort of stuff. It's surprising how little, how this looks the same with different technologies and stuff out there. So this is 4 megabytes of RAM, not gigabytes, megabytes of RAM, from like 1990s. Again, it has the memory chips in here, and then the pins where you slide this into your computer to use it. This is kind of a today version of that stuff. This is 1 gigabyte of RAM. Again, different number of pins here, but pins and the chips. We have chips on both sides now and stuff like that. So again, this is what your RAM is generally looking like. I thought I grabbed a smaller one. And then like in your laptop or something like that, it doesn't have quite a big thing, the form factor will be smaller and you'll get this kind of chip. Again, more similar pins, just a little closer together, and memory chips on them, right? So if you swapped out memory and anything, that's a pretty typical upgrade to like a laptop or something like that. You can unscrew some flap in the bottom, pop out the memory, or it might be just extra slot in some new memory. So, and you can buy, you have to look at, again, you have to know what type of memory it is, and then put in the same memory. Especially if you have 2 of them, 2 of these chips. A lot of computers will have like slots for 2 chips. You want to make sure both of them generally are the same speed and stuff like that for that. But again, this is a pretty common upgrade for memory. But again, has it. So this one's 2 gigabytes, and this is 4 megabytes. This is just older. But again, very similar idea for this. So I mean, the idea hasn't changed that, but we just shrunk them a lot. We just shrunk it a lot, and so now we're using what is called DDR5 RAM or SD-RAM for that. So as I'm going through this, you may want to grab the exercise and start working on that. So again, you might want to go into the exercise, grab that, make a copy of it. Okay. So we've got just go through and talk about some of this stuff. So we mentioned electricity there and volatile and non-volatile. So a lot of this memory needs electricity to keep it active here. And when electricity goes away, it stops working there. Now we do have non-volatile memory, and you'll probably see that with your SD cards. If I have it. But, or and I don't know if anyone still uses these. You probably used them before, the little USB flash or drive sticks or stuff like that. And again, when you open those up, it's just a memory. It looks just like a little memory, circuit in there. But again, this is non-volatile. So the way we store this information, it can hold that information even without the electricity there. So we don't need this whole circuit here to store the information. We make an actual change in this that stays there regardless of whether or not it has power for this. And this is an older memory stick. It's interesting, these memory sticks are all about the same size, but this is from about 20 years ago, and it's 255 megabytes there. And now I've got, I'm running a terabyte one, I think now, is my memory stick about like that, I think. So again, this physical size and look of it has not changed that much. But again, how much we can store, and it certainly has changed a lot. So, okay, let's jump and watch a little bit of our crash course video here, and especially when we talk about early storage technology for this. See that volume.
We've talked about computer several times in this series, and we've even designed some episode 6. In general, computer memory is non-permanent. If your Xbox accidentally gets unplugged and turns off, any data saved in memory is lost. For this reason, it's called volatile memory. What we haven't talked so much about this series is storage, which is a tad different. Any data written to storage, like a hard drive, will stay there until it's overwritten or deleted, even if the power goes out. It's non-volatile. It used to be that volatile memory was fast and non-volatile storage was slow. But as computing technologies have improved, this distinction is becoming less true, and the terms have started to blend together. Nowadays, we take for granted technologies like the simple USB stick, which offers gigabytes of memory reliable over long periods of time, all at no cost. But this wasn't always true. Punch cards, and its close cousin, punch paper tape. By the 1940s, punch cards were largely standardized into a grid of 80 columns and 12 rows.
These are punch cards.
966.
I'd like to brag that I'm not old enough. I never used punch cards. So that's not. Now, I will mention that this is mine. So I am this old, but not punch card old. So.
Data. That's the size of an average smartphone photo today. And punch cards were a useful supplement in storage for decades. They did take out. However, punch card was slow like lumps. You can't easily unpunch a hole. So they were less useful.
So when I was in high school, we had a high-tech high school, and we had punch card printer and a punch card reader in high school, and we were taught how to use it in high school there. And I purposely did not like that, so I skipped that class there. So I mean, that's how popular it was. It was taught in most schools.
And then discarded. A faster, larger, more flexible form of computer memory is needed. An early and practical approach was developed by J. Preston Ecker as he was finishing work on ENIAC in 1974. His invention was called delay line memory, and it worked like this. You take a tube and you fill it with liquid like mercury. Then you put a speaker at one end and a microphone at the other. When you pulse the speaker, it creates a pressure wave. This takes time to propagate to the other end of the tube, where it hits the microphone, converting it back into an electrical signal. And we can use this propagation delay to store data. Imagine that the presence of a pressure wave is a 1 and the absence of a pressure wave is 0. Our speaker can output a binary sequence like 10100111. The corresponding waves will travel down the tube in order, and a little while later hit the microphone, which converts the signal back into ones and zeros. If we create a circuit that connects the microphone to the speaker, plus a little amplifier to compensate for any loss, we can create a loop that stores data. The signal travelling along the wire is near instantaneous, so there's only ever one bit of data showing at any moment in time. But in the tube, you can store many bits. After working on ENIAC, Edgar and his colleague John Buckley set out to build a bigger and better computer called EDVAC, incorporating delay line memory. In total, the computer had 128 delay lines, each capable of storing 352 bits. That's a grand total of 45,000 bits in memory. Not too shabby for 1949. This allowed EDVAC to be one of the very earliest stored program computers, which we talked about in episode 10. However, a big drawback with delay line memory is that it can only take one bit of data from the tube at any given instant. If you wanted to access a specific bit, you'd have to wait for it to come around in the loop, what's called sequential or cyclic access memory. Whereas we really want random access memory, where we can access any bit at any time. It also proved challenging to increase the density of the memory. Packing weights closer together meant they were more easily mixed up. In response, new forms of delay line memory were invented, such as magneto-restricted delay lines. These delay lines use the metal wiring and twisted, creating little torsional waves of represented data. By forming a wire into a coil, you could store around 1,000 bits in a 1 foot by 1 foot square. However, delay line memory was largely obsolete by the mid-1950s, surpassed in performance, reliability, and cost by limited on block, magnetic core memory, which was constructed out of little magnetic donuts called cores. If you loop a wire around this core and run an electrical current through the wire, we can magnetize the core in a certain direction. If we turn the current off, the core will stay magnetized. If we pass current through the wire in the opposite direction, the magnetization direction, called polarity, flips the other way. In this way, we can store ones and zeros. One bit of memory isn't very useful, so these little donuts were arranged into grids. There were warnings for selecting the right row and column, and a wire that ran through every core, which could be used to read or write to bits. Here, in each of these little yellow squares, there are 32 rows of 32 columns and 20.
That's what I wanted to bring down. I have a little bit of core memory, and you can actually look at these tiny cores. They're only like that. Each little donut is only about that big.
Rolling one computer in 1953, which used a 32 by 32 core arrangement. And instead of just a single pane of cores like this, it was 16 boards deep, providing roughly 16,000 bits of storage. Importantly, unlike delay line memory, any bit could be accessed at any time. This was a killer feature, and magnetic core memory became the predominant random access memory technology for 2 decades, beginning in the mid-1950s, even though it was typically woven by hand. Although starting at roughly $1 per bit, the cost fell to around 1 cent per bit by the 1970s. Unfortunately, even 1 cent per bit isn't cheap enough for storage. As previously mentioned, an average smartphone photo is around 5 megabytes in size. That's roughly 40 million bits. Would you pay $400,000 to store a photo or core memory? If you have that kind of money to drop, did you know the crash course is on Patreon, right? Anyway, there was tremendous research into storage technologies happening at this time. By 1951, Eckert and Buckley had started their own company and designed a new computer called UNIVAC, one of the earliest commercially sold computers. It debuted with a new form of computer storage, magnetic tape. This was a long, thin, flexible strip of magnetic material stored in drills. The tape could be moved forwards or backwards inside of a machine called a tape drive. Inside is a light head which passes current through a round line.
So have you guys ever used anything that used a tape? Because that used to be very common there. When I was young, all music was stored on cassette tapes. Movies were stored on like VHS tapes there. Again, we often use magnetic tapes to store computer data. Have you ever used have you used a VHS? You have? Some of you have maybe seen them? Used them once at grandpa's house to watch something there. So, but again, We still use that term, I use, did you tape it? But again, I don't think anyone actually uses tapes, anymore. I don't have anything that can play a tape in my house. And I have some in my office for historical reasons, but, I don't really have much, there. I have lots of cool tape drives up in my office.
These wait to right underneath it to read and run through the data. It is the data stored as possible, drawn to rotate thousands of revenue minutes. By 1953, when the technology started to take off, nuclear units able to record 80,000 bits of data. That's 10 kilobytes. But the manufacture of drums ceased in the 1970s. However, magnetic drums did directly lead to the development of hard disk drives, which are very similar, but use a different geometry. Instead of a large cylinder, hard disks can develop disks that are hard, hence the name. The storage principle is the same. The surface of the disk is magnetic, allowing write and read heads to store and retrieve ones and zeros. The great thing about disks is that they are thin, so you can stack many of them together, providing a multi-surface area of data storage. That's exactly what IBM did for the world's first computing disk drive, the RAM 305.
Taking apart hard drives yet? But it's always fun. Still, you have a device that has a hard drive in it. You have a device, maybe? Because your computer or your laptop probably has an SD, solid state drive right now. When did the Xbox switch? Does the Xbox have a drive in it?
PlayStation.
Oh, yeah, maybe an old PlayStation. Like, so, yeah. Oh, yeah, this actually, this is from, 1994.
Expensive.
We used to have this on campus here.
No, not slow, which is cheap. This mixed approach strikes a balance between costs and hard disk drive rapidly improved and became commonplace by the 1970s. A hard disk drive like this can easily hold 1 terabyte of data today. That's 1 trillion bytes, or roughly 2.
My father-in-law, after World War II, he flew and did radios on a bomber in World War II. He came back to Minnesota, and so he knew some tech. And there wasn't that much. And so he started working for a company called IBM back then and worked on these huge hard drives that were like this big in the 40s and 50s there. And it was really cool talking about that day and how it's changed.
0.000000005 cents a bit. A huge improvement over core memory's 1 cent per bit. Also, modern drives have an average seek time of under 1/100th of a second. I should also bring you next to the close cousin of hard disks, the floppy disks, which is basically the same thing.
Oh, I miss floppy disks so much. Oh, what?
My dad has a lot of disks.
Yeah. Yeah, these were the ones, when I was in college, we lived in buying the these were, my college years.
Storage came into the scene in 1972, the 4 to 12 inch later. However, you're probably not anyone who's later smaller and more popular cousin, the compact disc or CD, as well as the DVD, which took on.
So have you used CDs? Music, did you grow up with music CDs? Yeah, good. And Blu-ray, what did you play movies with? What? Just like
Blu-ray player.
Yeah, Blu-ray player and maybe tape before that? No, what was before Blu-ray? Yeah, so. Okay, but again, how much of that do you have around now? How much do you have any music?
We still have like a VHS and Blu-ray.
Okay.
But we just keep them for the stuff.
Right, yeah. So, right, yeah, so, yeah. And it's kind of fun because some of the old LPs, people are still playing those kind of for historic, or, for that sort of idea, I think, here. Okay, so, describe some types of memory again and storage here and when they were used. we can look at the videos for that as you go through here. Now let's talk. I'm gonna go back here and get back to DDR sort of stuff here. So DDR means that we are doing double data rates. Originally we had single data rates where I don't know if we begin to see when I don't know if you remember when we did these circuits, we'd have a little clock circuit, and every time the clock circuit would go up, for example, we'd update the circuit there. So that's what's called a single data rate. But you can actually program the circuit so that every time your clock goes up or down, or up or down, you will update your circuit or change your values there. And so then you'll get twice as much data through our system. So DDR simply means that we have double data rate in our memory sort of stuff. Now, there are lots of different versions of DDR. We're currently on DDR 5 or 6 sort of idea. There are some other specialized versions of DDR, like graphic DDR, that's optimized for graphics and graphic cards for that stuff. So if you look at like A3 here, talks about some of this early memory stuff. And my question is, have you used any of this? And if so, where? So I'm sure you've not used magnetic core here, RAM memory, all that stuff. Static RAM, this is like what would be like in a flash drive, something that's solid, that's not volatile and stuff like that. So you probably have used this SRAM or static RAM here. It's actually a little different. Well, I guess that's more like flash memory. Static RAM is more for inside circuits, like maybe like in an appliance where when you turn it off and on, it'll remember. Like in your car, the fact that your car remembers what radio stations you have pre-programmed in, I think that might be stored in SRAM. Because it's just a couple things, a little bit of value, but again, it has to remember it. I think cars now, when you unplug your battery, do you lose your car radio stations? It used to be you did, but I don't think you do anymore. Sure. Yeah, so if you don't, it's probably using static RAM. Flash memory is again these they're sort of stuff. And then a DDR RAM is what you're probably using in your laptop, in your gaming machine, in your tablet, in your phone. All those are using some version of DDR memory, probably. So again, and so talk about any sort of device, describe which of these devices you may have used. And again, with DDR memory, I want you to think of two different devices for this A4 that are using DDR memory and work version. So you may have to do a little searching, ask AI or ask Google about this stuff, but probably, again, your phone, your tablet, your Xbox or PlayStation or Switch or whatever you have, all those are probably using DDR memory of some form here. So it's interesting it'd be worth looking at. Some of them might be using this graphics DDR memory. So like the Xbox has some GDDR memory in it. It also has some regular DDR memory for the system stuff here. So some of it, like an iPhone, a phone will use low power DDR, so it doesn't use as much power for this. So again, find two devices that you own that have some DDR memory in it. So, okay, I'm gonna go back here. So, talk a little bit about memory banks here. So DDR memory is usually stored in these memory banks here. And so a memory bank is like a whole set of memory together here. And with multiple banks, we can read. So normal memory, you can just read one bit at a time. But if you have like 8 banks, you could read 8 bits at the same time from different locations, one from each bank there. So sometimes we'll divide our memory, or memory is generally divided up into these sorts of banks and set up that way with these banks and these groups, and help with fetching. So with this A5, we talked a little bit about that. How there's some complicated addressing logic inside the chips that will spread out data. So if you're storing data, it'll actually store it in multiple banks so that you can read it all simultaneously. I don't think this description from the book is very good. So your job is to find a better description. So you can Google it, or AI will provide a pretty good description of this also. So provide a different description of how DDR banks are used and why they speed up memory access here. Okay, I'm going to go back to this text. Okay, let's talk about a little bit more then about I/O subsystems. So again, CPU, memory is right close there. Everything else it gets further away and slower. And that's what we usually call the I/O subsystem, input, output stuff. How do we get data and stuff and information in and out of our to our processor. So there's 2 kind of general ways of doing it: parallel and serial for that. Serial, and this used to be more common, would be like 1 or 2 pins that could have data, and you would send the data off and on here. You may have remember, and again, this is usually what's called a baud rate. And if you've ever watched old movies, you'll hear data sent over a phone line, beep, 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 and it'll actually hum at a certain different frequencies, and that's where and again, that's how we send data off and over like a audio line, is that we send 1 bit at a time and we just send it out even. Now, you can do the same thing with wire. You can have a single wire connected and you can send out data over that 1 bit at a time at a certain rate. With our Raspberry Pis, there are certain pins out there that are set up for serial interfaces. I think IC2 is the common one. And there are certain devices or sensors. I have a student doing a more advanced project with Raspberry Pi, and I think he's doing a air quality filter, and that filter, that sensor has to be connected to Raspberry Pi using this serial interface there. So there's some places that still use that serial interface, and but we found it much faster to use parallel interfaces. That's where you have a whole chip of you have a whole row of pins, and you're sending data on the whole row of pins there. And again, your hard drive probably has a row of pins on it. This is another old hard drive sort of stuff where you're doing a whole bunch of pins. So for a long time, we used this parallel interface for things because it was just faster. And then, but it was, all these cards are really big and lots. I mean, remember when you tried to connect all 40 pins on, it was just hard to get them all aligned, and the pin would break off. And so we've actually now moved away from parallel, gone back to serial. We just learned to speed serial up a lot more. And so like your USB sort of stuff, that just uses a couple pins and sends data very quickly on those. So let's look at some different kind of devices here for this. Originally, there was this PCI Express bus that could be used, and there are different versions of that came out there. For hard drives and things like that, we had SATA here. So again, if you look at old hard drives, some of them will have these these pin connections here that you can connect up for it. And some of them will have more SATA devices. So like this is again, so I want to connect this to USB. So this is a device. So let me plug it into a USB port, but let me plug in any old hard drive into this. So this is a hard drive, and let me see if I can. Okay. So again, on some old hard drives, we had these sorts of pins like this, where we had a whole set of pins. That's the older one. Then we moved to SATA. These are SATA, where again, we had a number of pins, but we had that many pins there. And again, this is just a SATA to USB interface, where I can take any hard drive and plug it in here and then connect it to my computer and read it for that stuff. So again, that's one type of interface we had. Getting focus right there. Okay. And then there's different versions, of course, of all these techniques here. Now, modern drive, so your laptop might still take a SATA drive in there. There might, if you unplug it, there might be a slot for your SATA drive for a drive like today, but much of that has been replaced in recent years by this M.2 or similar sort of stuff. So like this is what a hard drive looks like. Again, we switched much more to a solid state drive, so not a physical drive. I mean, this is just a case for one, but it's just let me switch back. So again, this is the old hard drive, right? I mean, this isn't a big one. This might be in your laptop. If you have an older laptop, you might have one like this there, but more likely this is your new solid state hard drive, right? And again, very small pins here and all solid state for that. So no physical device for that. It's interesting to note, which iPod did you first have? Did you have an iPod to play music? No? Well, the original iPods were this size, and the reason why is because most of them were simply a hard drive to store music with a little bit around it. So this was the form factor that Apple designed their iPod for, and that evolved into the iPad, and the phone. And so I think this size largely dictates what's in our phone, what the size of our phones today. Where yeah, this is now our current memory for that stuff. So okay, let's go back to here. Okay, so that's this M2. Let's see how we're doing on this. So DDR. I'm going to skip over this command line stuff for a little bit. Again, part C. I want you to find a photo of a PCI bus expansion slots and an expansion card there. Again, you're not going to see these much anymore. but you might. I was just at my church this last summer and I had to plug in a new video, or we needed to connect some audio digitizer to an old computer. So we actually used a PCI card for that here for this. So these are cards that'll slide in slots of a big computer, of an old computer system here. Okay, the SATA disk interface, find a description or photo of a SATA connection for a hard drive. And again, there's two modern hard drives work off of either the M.2 or the NVMe standard. So see if you can find a drive. So again, often you look at your laptop and inside you'll see what kind of chips it'll take. And it'll take either, or you look at the specification, an M2 drive or an NVMe. You go to Amazon and you'll look at for that sort of drive. So your job is to go to Amazon. Search for one of these NVMe drive here and find one. Here, and same for an M2 hard drive. So what's the storage capacity? What's the I want the URL there, and then the storage capacity and the cost from it. So then let's talk USB here. I just rearranged my USB cord drawer at home because we've now moved a lot to USB-C to USB-C there rather than USB-A to USB-C sort of cords on this. So let's talk a little bit about the different kinds of USB connections, and I want you for the exercise to find a photo showing the different size connections, right? So, so you're familiar with the classic USB, or what I call USB-A connection here, the big chunky one that has to go in only a certain direction, right? There. And now you might not be familiar with some of the other ends of this, depending on what you're plugging in. There'll be different other plugs available for this. But I would guess most of your devices now are USB-C plug-in. So iPhones move that way. Most phones are, think of what, so USB is the nice, right, circular kind, or I don't know, oval version that's out there for that. So yeah, let's see. So like my headphones have a USB-C plug in it, right? To charge that up here. So I think, and again, we used to work a lot with USB-C to USB-A, and I have a lot of cables like that. But now it seems like we're moving more towards USB-C on both ends of the cable and doing that a lot more for devices. There's micro USB. I had to charge up an old power bank, and that was micro USB stuff. So there are still some other, devices out, some other USB connections out there that are, older for that. But so again, find a good picture of that for that. Now let's talk colors. So often the little plastic thing in the USB-C or not the USB, but the USB-C will be a different color. Like this one's white, but they might be blue. Have you seen, do you know what blue is and white is? So there's different versions of USB. So a faster version than the standard one is USB 3. Yeah, right. Which is what most laptops are doing. So if you look for like what is the blue USB port. So a blue generally means that it's a USB 3.0 port on a computer or something like that. So like we have we'll talk about VR sets. We have a VR headset that has to be plugged in, it has to be plugged into two USB-C 3 ports. And so in a computer we have some that are just normal ports and some that are blue ports. And so we have to make sure when we're plugging the headset in, it has to be plugged into one of the blue ports because it needs the speed that USB-C 3.0 provides here. Now I have a fast charger that charges my tablet very fast, and its cord and its ports are all orange because it's a high amp charger there. So sometimes you'll see cords that will be a certain colors denoting that they can take a high amperage or fast charging ports for this. So I want you to see if you can find an image that shows different colors of USB-C ports. Again, it can show the traditional USB ones or the USB-C ones. On most computers, USB-C ones are automatically 3.0 ports. So you don't necessarily have to worry about those being blue for that. So. And then we want you to look at the computers and how we connect the videos up to the computers here. And you can think about our Raspberry Pis also and how we're connecting the monitors to the Pis here. So unfortunately, there's way too many options on the video end of things. So the oldest way is probably this, what I call a VGA port, this sort of port like this for VGA. And older systems will have this sort of video in and out port for it. They may also have, and this isn't a great view of it, a digital port like this. It has one thing that's vertical lines and a different number of pins, or they might not have all this doesn't have all the pins, but it'll have some of the pins or parts in it there. So those are older versions. More digital versions now are the HDMI. So, traditional HDMI port, this is an adapter for I think this is a mini port. Your Raspberry Pi likely runs off of a micro HDMI port. So you might have a cable that goes from HDMI to even smaller than this, a very small micro HDMI port for it. So there's different versions of that that'll run. So why don't you look at the monitors here and see what ports are available for those monitors here. Does it have a VGA port? Does it have a DVI port? That was the second port. Does it have an HDMI port? Let's talk display port. So again, HP decided at some point, we're going to make our own monitors and computers and try to only sell them to our people and lock businesses in them. So they made their own cables and video plug called a display port just for HP computers there. So you'll see display port. So it looks a lot like HDMI port, but HDMI ports are rounded kind of on both ends. Display ports are square on one end and rounded on the other end. So you'll see display ports out there on some computers there. So if you turn over, if you look at one of these monitors in class, you should be able to see what kind of ports are available to it. In the same way, like when you look at a monitor like this big monitor, it's on this slide, you'll see what it has as far as HDMI ports and stuff like that. Yeah, so here's the HDMI ports, and that sort of stuff. There's a whole bunch of different ports, not just HDMI, but video, composite video and stuff like that in and out of those for that. Last thing I want to talk about then is VR sort of stuff. Have you used a VR headset? Yeah, for something. We have an Oculus Rift, still old, but still works okay. Upstairs, and we do some the computer club and stuff. We'll use that sometimes in game design. There's a lot of new technologies here. So I just want you to select one of the common modern VR headsets and display it here. I just want to show you where we've come from here. So this is an original Oculus development kit from a few years ago. And you can just see it. They basically just took a regular screen, a rectangular flat screen, put it on there, and then put some really big lenses in here to make you see only parts of that screen in a certain way. So it's all done with lenses and a big flat screen here. It all had to be plugged in. It's running off of a DVI port cords here. It has an interface box in here for this. And it did not have really any motion detection on it, or very little motion detection on it. Just I think a simple tilt detector was all it had for it and how it worked. And so you compare that what that was, and it'll be interesting to see because we've been promising this for 20 years there, and so it'll be interesting to see if we get that anytime soon or what we get. But I just wanted to show you that we have in the last 5 years come a fair amount. So this again, this is an Oculus, and so Oculus was bought out by Facebook, and so the current Meta version is the evolution of that technology. And again, one of the questions is it wired or not? And there's now moving a lot more towards non-wired versions of this sort of stuff. So when you look at these, pay attention. Are they wired? What are they? How are they connected up? And things like that. So. Okay, I'm going to jump back into the textbook for a little bit. Okay, we talked about the USB interface and different versions of that. Again, generations, we started about USB 1, USB 2, USB 3 there, and you can just kind of notice the speeds of this, where USB 1 transfers at 1.5 megabytes per second. USB like 3 now is transferring about 2,000 megabytes per second. I don't know if you've ever plugged in one of these drives and tried to transfer a large file and it's really slow. It probably means that either the drive or the plug you're plugging into is not a USB 3 version of it if it's taking so long to transfer things on here. a lot of proprietary, companies have their own things. So Thunderbolt, I believe, was an Apple alternative for many years for this. Again, and then we get into these graphic displays here. I'm going to skip over the network stuff for now. We'll spend another week on networking at another time and talk about Wi-Fi and that sort of stuff. Again, mouse and keyboards used to be serial kind of plugins. Now they're largely USB. Like all these in the labs here are USB. But now is thinking do you have an external keyboard and mouse? And do you have a Bluetooth one or is it plugged in? So in my office, I have a Bluetooth one, but at home, like at my office, I have a plugged in one, but at home, I have a Bluetooth one that I use for that connects up there. So again, ask yourself, what physical connections are you making? And so much of this stuff is moving away from this. Not only that is, as far as like storing stuff on things, I was just reminded, I was using an old camera this last week, taking pictures. It would put them on an SD card. I would have to take it, and then I'd take the SD card out, plug it into my computer, and copy the photos over to my computer, and then upload them to share them. There. I was doing that for about half my photos. About half my photos, I was just taking it on my phone, and it would automatically be uploading it to Google Photo as soon as I took it and was online there. So again, it made me think about how, we've moved so much away from these little cards or drives or anything. I mean, I no longer use anything like this because everything I store, if I want it here in my home computer, it's up on the cloud there. And that's one of the reasons why we're doing all these extra stuff on cloud stuff, because almost all this stuff that like we're talking about here is largely being replaced with cloud technology here and connection. So, what do your music, do you, rather than musical CDs, your videos, your photos, how many of those are on actual devices that you own and how many are uploaded or stored in the cloud now for you and automatically for that? Okay, let's see. I'm going to jump in here and talk a little bit about command line interfaces. I'm going to play this video, and then we're going to type in some commands here. And again, you've already done the lab kind of related to this, so this should all seem familiar. So I'm going to play this video. Then you're going to want to come up with 3 commands, and we're going to play this adventure game and then try out PowerShell and DOS command window and try out some different commands on that here. So I'm going to play this video.
If a man really hated ads, here's what he would do. Day 1, he would install Pi on his computer without spending a dime.
It's the way to interesting.
So I'll just note, since we saw that ad, is that we will look, you have to do a project on your Raspberry Pi at the end of the class, and one of them is an ad blocker that you can use your Raspberry Pi for. So,
but even when the only interaction was through text, programs found a way to make it fun. Early interactive text-based displays with famous types like all created in 1977. Players of these sorts of early games were expected to engage their limited imagination as they visualize the fictional world around them. Like what terrifying monster confronted them, but it was pitch black and were likely to come from over it. Let's go back to our command line, now on a fancy screen-based terminal instead. Just like before, we could see it in our current directory with the ls command. Then let's go into our games directory by using the cd command with change directory. Now we can use our ls command again to see what games are installed on that computer. Sweet, we have Adventure. All we have to do to run this program is type its name. Until this application portal will quit it, it takes over the command line. What you're seeing here is actual interaction from Colossal Cave Adventure, first developed by Will Prather in 1976. In the game, players can type in 1 or 2 word commands to move around, interact with objects, fix items, and so on. Program activities rated describing locations, possible actions, and the result of those actions. Certain ones resulted in death. The original version only had 66 locations to explore, but it's widely considered to be the first example of interactive fiction. These text adventure games later became popular with Mutt or multi the dungeon, and they're the great forebearers of the autographical MMORPGs we enjoy today. And if you want to know more about the history of these and other games, there's a whole series on it hosted by Andre.
So again, part of me for nostalgia wants to just teach you command line interfaces because again, that's what I grew up with. That was the only way to interact with the computer. But in reality, it is actually useful to know some command line interfaces. Often when you are working even on the cloud, we'll see when you're setting up a cloud environment and a virtual machine on the cloud, often you'll just be given a simple command line interface to the cloud, or at least if you can do something with command line interface, it makes it much easier for basic things, how to install and set up stuff for that. Even today, when we're building and compiling things, a lot of times it's easier to do things at the command line than it is. So like when we are using programming in VS Code, there's a terminal window, and sometimes it's just easier to type in commands into the terminal to do certain things than to try to work through the whole menu system for that. So again, command lines are still important. So we're going to try out a couple of things. The first we're going to try out is this online version of Adventure. So if you click on the little blue adventure game, it'll open up to this window, and you want to say play Colossal Cave Adventure on the web. Play Colossal Cave Adventure on the web, and it'll do a simulated interface here. This is about, would you like instructions? I'm going to say yes. Somewhere nearby in Colossal Cave, I'll be your eyes and ears. Direct me with commands of 1 or 2 words. I should warn you that I only look at the first 5 letters of each word here. So you'll have to enter northeast as NE or something like that for this. So what next? So you're standing at the end of a road before a small brick building. Around you is a forest. A small stream flows out of the building and down the gully. So can I try explore? Stream. You're in the valley in the forest besides the stream tumbling along the rocky bed. Go to forest. In the open forest with the deep valley on one side. To valley. So you can try these different things. And again, I think, I don't know if you can say go north here or not. Right. So you're exploring this. It's called Colossal Cave. So one hint might be to find the cave and not, that would be a good place to go there. So your job is to try this out and explore this. We want 2 commands from Adventure that you used here. So. The thing we're going to try out is on Windows, there are 2 different command lines. So I'm going to go over here and I'm going to type CMD for command and bring up the command prompt, which will be this little black command window. And then I also want to bring up the new version, which is PowerShell. So I'm going to start typing power and make sure I select PowerShell, not PowerPoint or something like that. I want to select PowerShell. Oh, PowerShell is no longer blue. It's really disappointing. Okay, that's sad. Okay, it used to be blue here for PowerShell, but they've changed it. Right? So we want to work on some different commands here. So let me see if I can get these side by side. There. So they should tell me what folder I'm in. So I'm in /user/T Gibbons here. So that basically means that if I look in my folders, and it's like C colon. So if I look at my PC, there's the C drive. If I go inside the C drive, there's the users drive. If I go in there, there's the T Gibbons drive, and that's where I'm at. I'm in, and again, if I click up here, I'll see the same thing: C:/user/T Gibbons, meaning I'm in the C drive, I'm in the users folder, and with that, I'm in the T Gibbons folder. So that's what is showing me with the prompt on both of these. Now I can try to list out the files in there. So in Unix, like system listing files is ls here. So that will, with PowerShell, that'll work, and it should, but with command prompt, the older DOS prompt, it doesn't. I have to type in dir to get a listing of files for that. So dir is short for directory, or ls for list files here. And again, it should list out the same sort of stuff as in my folder kind of view here for this. So in both of these, I might want to change what directory I'm in so I can CD to a directory. So maybe I want to CD to documents. I'm going to say CD space documents. And over here, CD space documents. So commands like CD in Windows, you can type it in uppercase or lowercase. So I can have capital CD space documents or lowercase CD documents. Both work fine here. And again, I can type in ls to list off the files, or if I'm in the command prompt, dir. So your job now is to start up these two shells and describe 5 different commands you can use and what they are in DOS command shell and PowerShell. The first one is display help here. So I can say help and then a command, or man for manual in command. So, and I think if I just type in help by itself, it'll list off a bunch of commands. Now, one thing you'll find is that, in this command line interface, sometimes it'll display multiple pages of text. And there's not a scroll bar. Well, there is on this, but in traditional ones, there weren't a scroll bar. So they would display one page and then they'll ask you it'll say more, and then you can hit space and it'll display another page of text, and then space will get you to the next page of text for that. There are commands to make folders, to change directories, to copy directories, things like that. So. I'm going to wrap up. If you have questions on this, call me over. I'll wander around and see if you have any questions on this. So remember, exercise is not due till Sunday, so you can turn in anytime between now and Sunday night. Okay.